Welcome to This Explainer. Today, we're unpacking a mathematical mystery that's literally hidden in plain sight on practically every world map you've ever seen. If you've ever stared at an in-flight screen and wondered about the bizarre, sweeping route your plane is taking, you are in the exact right place. We're going to completely rethink the geometry of how we travel across the globe.
So, why do seemingly straight paths on a map actually take longer to travel? We've all done it. You look at a map, draw a perfectly straight line from point A to point B, and think, yep, that's definitely the fastest way. But actual flight paths look like these massive, unnecessary arcs. It kind of feels like a giant cartographic illusion, doesn't it?
Okay, let's dive into this cartographic illusion and how flat maps deceive us. Because the reality is, the maps we use every day are fundamentally tricking us.
They distort true physical distances just to make a 3D globe fit neatly onto a 2D grid. So, to bust this incredibly common myth, we have to completely throw out our two-dimensional thinking. Straight lines on a flat map are not the shortest distances in reality. To figure out the true shortest distance, we literally have to start looking at the globe as what it actually is, a three-dimensional sphere.
The foundation of navigating our planet rests entirely on the critical distinction between what mathematicians call great circles and small circles. Looking at the mathematical geometry on a sphere, you can clearly see the equator cutting across the middle and those vertical meridians slicing straight from the north to the south pole.
Moving into the geometry of the sphere, let's categorize these circles. We're going to break down the foundational rules that govern these paths.
Let's compare them directly. A great circle is any circle where its center perfectly matches the center of the sphere itself. Think of the equator or those full meridian rings. On the flip side, small circles happen when a plane cuts through the sphere but totally misses the center. Pretty much every single line of latitude, except for the equator, is a small circle.
Which brings us to a vital vocabulary word for any navigator, the geodesic. This is an arc that travels strictly along a great circle, and it represents the absolute shortest physical distance between any two surface points. If you want to save fuel, time, and distance, you absolutely want to be on a geodesic.
All right, on to the mathematical breakdown. Let's look at the variables and formulas, because we wouldn't just tell you geodesics are shorter without actually proving it.
We just need three essential parameters to follow the math here. Capital R is simply the radius of our planet. Theta is the latitude angle, so how far north or south you are relative to the equator, and phi is the central longitudinal angle, which basically represents the horizontal span between your starting and ending points. Let's move on and see how this builds our formulas. For a small circle, like your standard line of latitude, the arc length is just the radius times the cosine of your latitude multiplied by that horizontal span. But for a great circle, something fascinating happens. That central angle actually contracts. The factor adjusts to 1 minus 2 theta. So the great circle arc length is the radius times 1 minus 2 theta times the horizontal span. Next up, the ratio of distance, small versus great circles. If we take those two formulas and compare them, we get to reveal the core mathematical takeaway that solves this whole mystery.
So the crucial point is this beautifully simplified ratio. By stripping away the shared variables, it boils down entirely to the cosine of theta compared to 1 minus 2 theta. This single ratio is literally the mathematical engine behind global navigation.
Testing the extremes at the equator. The best way to trust the math ratio is to push it to its limits, right? So let's apply this right at the equator, where our latitude angle, theta, is exactly 0.
When you plug a latitude of 0 into our ratio, both sides equal 1. The cosine of 0 is 1, and 1 minus 2 times 0 is 1. This is a phenomenon called equatorial alignment. Because the ratio is a perfect 1-to-1, it proves mathematically that the equator is uniquely both a line of latitude and a perfect great circle. There is zero distortion there. Let's talk about the cartographic impact on navigation. Connecting this math back to the real world shows exactly why this geometry is a total game changer for pilots and navigators everywhere.
As your latitude increases toward the poles, the curvature distortion grows significantly. This is known as latitudinal deviation. In plain English, the further north or south you go from the equator, the great circle distance decreases much slower than the small circle distance. You get massive efficiency gains up near the poles when you choose a great circle geodesic over a straight line of latitude.
To summarize the cartographic impact, navigating straight along those horizontal latitude lines mathematically takes way longer. Our flat maps completely obscure this geometric efficiency. It creates this powerful illusion where highly curved routes on paper look drastically out of the way when they are in fact physically shorter on the actual globe.
And this brilliantly illustrates the mathematical comparison. You can clearly see how the great circle path completely outpaces the small circle path in efficiency. The math ratio we just explored proves exactly why that happens, even if the flight path seems to dip dramatically away from the straight latitude line.
We've officially busted our flat map bias today. You now have the mathematical proof that the shortest path between 2 points on our planet is almost never a straight line on a piece of paper. Knowing that flat maps constantly obscure reality, how will you picture the world differently the next time you book a flight? Keep that hidden geometry in mind and happy travels.